Sir currently serve as a visiting professor cum outreach advisor at Indian Institute of Technology, Dharwad. In this role, he also coordinates the GYAN program, Global Initiative of Academic Networks program, fostering international collaboration and academic excellence. Professor Jayakumar sir illustrates career over 4 decades. He has held various esteemed positions, including Professor HAG and Dean at the National Institute of Technology, Warangal. His research interest includes hydrology, water resource management, climate change adaptation, and environmental management. Beyond academia, he contributes significantly to the environmental conservation as a member of the governing body of Wetland International South Asia. So please join me in welcoming Professor K.V. Jayakumar sir.
Thank
Over
you.
to you, sir.
Yeah, thank you. So I'm very happy to be part of this GYAN program, and let me share my presentation.
Sure, sir.
Is my screen visible?
Yes, sir. Yes, sir.
Yeah. Is it visible, right?
Yes, sir. Yes, sir.
Great. Yeah, welcome to this talk, the participants from various institutions. And next 1 hour, I'm going to talk on droughts, especially to climate change perspective, and giving a couple of case studies which I had carried out in the past 4 or 5 years on drought. Let's start with working on water resource. I'm a 1978 graduate, and not too many people are interested to work in water resource. Civil engineering means structural engineering, geotech. So some of us decided to work in water, and that was the time a very beautiful quotation I read by John F. Kennedy in 1962, when at the time of Nobel Prize Award ceremony, he made his speech. One to solve the problem of water should be awarded 2 Nobel Prizes, one for science and other one for peace. Today, you find people fighting for water everywhere. Of late, we also know the Indus river being shared with Pakistan and India. We have a problem there. So solving water problem is a very important thing that has been attracting attention of the world. Now, as engineers, there is something which it's a Venn diagram which shows that you love what you love doing. You love civil engineering, you love water resources, and you're good in that, and you're getting a job in the same field, and the world also needs such people. So the intersection of what you love doing and what you're good at is called passion. Intersection of what you're good at and what you get paid for, that's profession. And intersection of what you can be paid for and what the world needs, a vocation. And what you love doing is the same as world needs, they're called mission. So today we need whatever you do, you love whatever you're doing, you must be good in whatever you're doing, and you get a job in your area, your specialization. And world needs a lot of good people today. And there's a time when civil engineering is not having the importance that it really deserves, but you find 5 years from now, all of us will be in great demand. Now, look at the amount of water that is available in the world. The total water available in the world is 96.5% is in ocean, and you find 2.5% is fresh water. If you expand this fresh water, you will find only 1.2% of the fresh water is the surface and other fresh water. If you expand this, you find in the fresh water, you find most of it is in ground ice and permanently frost. You got 20.9% lake, but just look at the rivers are 0.49%. The swamps and marshes are 2.6%, much higher. The amount of water in the soil is about 3.8%, atmosphere 3%. You find rivers have only 0.49% of the 1.2% of the fresh water, of the 2.5% of the total water available. So this shows that the amount of actual water available for us is very, very limited, but then that is enough to meet all our needs if we properly manage. So just look here, you find that's the total amount of water available, and that's the amount of liquid fresh water, and a small dot here is the fresh water of lake that's available to us. So this was a picture given in the year 1993, which is still valid. There's not much of changes taking place. Now look at our country. The area of our country is 329 million hectares. It has got 12 major and 14 medium river basins. 4% total average runoff of the world is in India. And per capita availability of natural runoff is just about 2,000 cubic meters per year. It's about 1/3 of the per capita availability in USA and Japan. And you find as the population increases, the per capita available water will keep decreasing. So this is something which all of us have to keep in mind, that we have less just equal to or less than 2,000 cubic meter per year per capita. Now, if you look at the rainfall that comes here, our annual precipitation is about 4,000 cubic kilometer. How did this come? This comes from the area of India and multiplied by about 1,100 millimeters of average rainfall, because annual precipitation is around 4,000 cubic kilometer. And the average annual runoff in various river countries is around 2,030 cubic kilometer, which includes surface and groundwater. And 80 to 90% annual runoff occurs during monsoon months, which is June to September. Even this is now changing. The total number of rainy days have drastically reduced now. The climate change impact, the rainfall, the onset starts late, the withdrawal starts early. The total rainfall comes in less number of days, causing floods during the rainy season and drought for the long extended period. So you find the potential water available in India is only around 1,800 cubic kilometer, out of which only 1,140 cubic kilometer can be put to beneficial use by conventional methods. So this calls for better water management, and groundwater availability is around 450 cubic kilometers. So that is the amount of water that's available to us. And this, I'm just creating a base for the talk. Now, if you see the rainfall pattern also, it is erratic in space as well as in time. This year, interestingly, the India Meteorology Department has predicted that there will be early monsoon. It could start maybe the last week of May, and early withdrawal. Sometime in the middle of September, the rainfall might stop. So that is a prediction which most of the past 10 years, our forecast has been reasonably good. So we're able to predict these things well in advance. The average rainfall in the country is around 1,100 millimeters, but it varies from about 11,000 millimeters in the northeast part of the country to about 215 millimeters in the western desert region. That means there's a very, very wide variability of rainfall, annual rainfall in the country. 11,000, it's actually now crossing 11,000 in Meghalaya area, and just about 250 millimeters, the western desert region of Rajasthan, and that is Jaisalmer region is around 250. You can see so around 40 times is the variation. And of this, 75 to 90% rainfall occurs during 25 to 69 rainy days during 4 monsoon months of June to September. That means, though our rainy season is 120 days, 4 months, the number of rainy days is between 25 to 70 in this season. That means the water management in India is very different. There's 60 days of rainfall. You have to store to use for the remaining 300 days. So it's not easy. It's one of the very difficult situations that we have. And you also find the coefficient of variation is more than 20% in most parts of the country. Coefficient of variation is standard deviation by mean, as an expressed percentage. It is more than 20% in most parts of the country. That means so year to year, it changes very, very largely. What happened last year is different from what happened this year, could be what could happen in the future. So this rainfall pattern is also to be understood, and it is very, very complicated rainfall pattern that we have. Now, if you look at the droughts, that's what I'm going to talk about in the next 1 hour, that some details. about the regions where the drought comes. In Assam region, the drought is very rare, once in 15 years. Assam includes the northeast as well. And you go to West Bengal, you go to Madhya Pradesh, you go to Konkan area, you go to coastal Andhra Pradesh, Maharashtra, Kerala, Bihar, Orissa is on an average once in 5 years. Then you go to the south interior Karnataka, eastern part of Uttar Pradesh, Vidarbha, is Nagpur area, Gujarat, eastern Rajasthan, western UP, Tamil Nadu, Kashmir, and the Rayalaseema AP, and the whole of Telangana. The average drought is once in 4 years, and western Rajasthan is once in 2.5 years. That means if you take the whole country, you find the drought periodicity is approximately once in 2 years to once in 15 years, depending on which part of the country we are considering. Now you can look at the global water consumption. Here there are a few maps. The top one is for the whole world, and here for Asia, you got Europe, and the last one is in Australia, etc. You find there's amount of water consumption is increasing. This is up to this year, which was prepared, and you also find we use water for lots of other things. So you find that the water consumption has been increasing across the world. Now, if you look at the amount of water quantities available, you find that it's all in square kilometers. You find the total fresh water in the rivers, 0.006% of the fresh water available. So you find that the amount of water that we do have is very, very limited. You see here, only 2.5% of total available is available in the fresh water. So this is some statistic prepared in the 1978. It's a very beautiful book, Water Balance, the Water is the Earth, and has not changed much. Now we also talk about sustainable development. This is very, very important nowadays in the keeping the hydrologic extremes. Sustainable development is very, very important. Very interesting definition given by Madam Brundtland, who was the Prime Minister of Norway in 1987, meeting the needs of the present without compromising the ability of the future generation to meet their own needs. It's a very beautiful definition. Now, when you talk about sustainability, we ought to talk about 5 different types of conditions. One is technical, the effective and efficient design and management of resource development projects involving balancing variable demands and supplies. So when you manage water, we have to have an effective, efficient design of the management of the water resource project. We'll talk about demand and supply. Very important. That environmental condition is that there shall not be any long-term irreversible effects. Financial sustainability, the cost of all resource development and management projects must be recoverable. Society must be support and be willing to pay for the services provided by the developmental projects, and we should have institutional mechanism to plan, manage, monitor, and adopt a changing situation. Like all of us are part of this. We as academicians and people working in the government departments, both state and central, are all involved in these type of things. So anything that we do must be sustainable with respect to technical, environmental, financial, social, and institutional aspects. Now, when we study hydrology, we try to provide answer to some other questions. What is the maximum probable flood at a proposed dam site? When you talk about water yield, how does it vary in the catchment from season to season and from year to year? This is very important when you talk about hydrological extreme. What's the relation between a catchment surface and groundwater resources? When you evaluate low flow characteristics, what low flow level can be expected to exceed 90% of the time? If given the natural variability of stream flows, what's the appropriate size of an in-stream storage reservoir? What type of hardware and software are needed for real-time flood forecasting and drought analysis? Now, this map was prepared in the year 1999 when we are just entering the millennium. Now, look at this. In the year 1950, you look at this map, the dark color shows that is low amount of water. Light color shows there is there's no problem. So look at 1950, just when India got independence, we are slightly in a lighter color. And 1995, a lot of development took place, population increase, became darker, and the same trend continues. This year, this has been projected to be in this color, that is dark color here. If I started from Bangladesh to India, to Pakistan, Afghanistan, then the whole Iran, Iraq, etc., the whole Gulf countries, and northern part of Africa is going to have catastrophically low amount of water. Catastrophically low amount of water means less than 1,000 cubic meter per head per year. So this is what is projected in the year 1999, which is not accepted major part of the world. And if I look at the United States, they are okay, slightly better. You go to Australia, is in this color. Okay, so you find that this was the map prepared in the year 1999, which was not accepted by many parts of the world. This map was revised by the International Water Management Institute at Colombo. And you find here that the blue color says there is no water scarcity at all. Now, the whole of the United States, the whole of Russia, most of the part of Europe are having no problem at all. Whereas you look at countries like India, India, China, the northern, the Gulf country, the whole of Africa, the whole of Australia, whole of South America, they are all having problem. The red color shows there is physical water scarcity. That means there is not water available to meet the demand. And the yellow color on the coastal areas, including Australia, say the economic water scarcity. Economic water scarcity means water is available but no money to develop. So this was prepared in the year 2005 by the International Water Management Institute of Sri Lanka. And this was again, there was some issue, many countries not accepting it because Australia comes under this category. But Australia, you find, except the eastern part, many parts are not livable. So they have to redo the map. And this map another map was prepared in the year 2013, which is today accepted for most of the development activities across the world. Now look at the map. There is a line here. It says how much water is available in cubic meters. Okay, now for example, look at India. India is in this color. India water stressed to water availability. That means India's water availability is between 1,000 cubic meter per head per year to 2,500 cubic meter per head per year. So you find China, India, Pakistan, Afghanistan, Iran, Iraq, etc. And then many countries here all are water stressed or water vulnerable. And countries in this color, blue color, say there is no water problem at all. The whole of Russia, whole of Japan, many part of Europe, the whole of America, North and South, whole of Australia, and many parts of Europe, Africa, are not going to face problem. There is plenty of water. So this is the map prepared in the year 2013, which is now the basis for most studies that is taking place. Now, just prior to that, another map was prepared. There is plenty of water available. Where is the water stress? Now look at India. If I meet the drinking water supply to everybody in the country at whatever, we have fixed some standard as 135 liters per head per day. If I give water to the whole country, I'm going to have problem for irrigation. That is water going to stress for irrigation. Now the white color shows there's no stress at all anywhere. Even US, you find the western part of US has stress for irrigation. And after meeting domestic irrigation, etc., there is going to be shortage of industry. The red color says, to meet all the demand, is sort of industry, even in US. And there are some places in the world that we are going to have even water stress for domestic. You find some small areas here and there, you find domestic, there's a problem. So this is another map that is prepared, which I think we should understand. Now, let us come to the topic that I'm going to talk about, drought. So drought is a prolonged shortage of water supply, whether atmospheric, that is below average precipitation, surface water, or groundwater. That means this is a general definition that we have. Now this drought can last for months or years, and maybe declare even for a short period of 15 days, like that's happened in our country. It can have substantial impact on ecosystem and agriculture, of affected region and can harm to the local economy. So drought has a serious issue that it can have on the economy, it can have impact on agriculture, and it can harm the ecosystem of the local region. Now, annual dry season in the tropics is in between the Tropic of Cancer and Tropic of Capricorn, and this significantly increase the chance of drought developing and subsequent bushfires. Like, too much of drought also catches forest fires, and the periods of heat can significantly worsen drought conditions by too much of evaporation of water vapors. That means water gets evaporated too much, there is no water. These are some pictures that I put here. Now, drought can be classified into different categories that I put here. One is the meteorological drought, when the rainfall is much less than the normal annual rainfall. It can be called a hydrological drought when the amount of stream flow is much less than the normal stream flow that you have. Now, which causes loss to the agriculture. It can cause loss to economy. Then you got another loss which is called agriculture drought, when the water is not able to meet the crop water requirement. Now, all this put together can have another type of drought called socioeconomic. So these can affect the society, it can affect the economy. So you find another socioeconomic drought is also possible. So drought generally can be classified into a meteorological drought depending on the rainfall, a hydrological drought depending on the stream flow, agriculture drought depending on the meeting of crop water requirement, and socioeconomic drought, the impact of these drought on the region. So that's how droughts generally can be classified. So you find the impact increase over time, reduced precipitation causes less water into the ground, then you have higher temperature and winds, lower relative humidity, greater sunshine, that causes to increase water loss from plants, land, and ocean. Agriculture drought, reduced soil moisture, crops suffer from reduced yield. This causes hydrological drought, reduced water in the streams and lakes and rivers, and reduced the wildlife gets stressed. All this causes the socio-economic drought. Demand of economic goods exceeds supply, then it affects the community and economy. You find over time these things happen. So meteorological drought cause agriculture drought, cause hydrological drought, and all this can cause socio-economic drought. So that's a drought that we try to understand. So you find the drought characteristics can be classified in terms of duration. How long is the drought going to last? The severity, what is it, how much is the deficit? Then the peak or the maximum value of the deficit that you have, the intensity of the drought, the spatial, how it is going to spread over time, and the onset and termination. The onset is when the drought is starting and when the drought is ending. Now, if a country like India, you find the onset of monsoon decides, the first monsoon in India comes in the Kerala border. So it depends on the first date of monsoon, the withdrawal of monsoon decides whether the country is having normal annual rainfall or not. For example, the past studies, about 100 years of records of India, rainfall records, show that whenever the first rainfall in Kerala is between 25th of May to 31st of May, the whole country is going to have a normal annual rainfall. If the first rainfall comes after June 10th, the whole country is going to have drought. And the rainfall comes before 25th of May, South India is going to have good rainfall, North India will get less rainfall. This is based on the past record, pure statistics. So the first rainfall Kerala decides when the country is going to have normal monsoon or not. Now this year, IMD has predicted that the monsoon is going to be early, maybe 28th, 29th of May. We might get the first shower. Already some summer showers have started. You find we might have the first rainfall somewhere on 28th or 29th of May, which indicates that the whole country is going to have normal rainfall. It's a very good prediction. Hopefully, it works. Then, what are the effect of drought, adverse effect of drought due to climate change? You find due to deficit rainfall, the higher requirement of irrigation management. That means you need more irrigation, and irregular rainfall, change in temperature has adverse effect on the crop yield, loss in economy. There will be loss in the yield. Then there is going less water storage, lower storage due to decreased flow in river and scanty rainfall. Then there is less soil moisture due to less rainfall, lower infiltration, and you have prolonged period of scanty rainfall. Again, less rainfall means that. Then more temperature increases in the evapotranspiration. You find that's how you find all types of effects. You'll find loss in yield, less water storage, less soil moisture, less rainfall, increase in evapotranspiration, more irrigation, and it goes on. So you find there are many negative adverse impacts of drought due to climate change. So these droughts are measured with many indices. You can go to the literature, and depending on the type of drought that we have, depending on the type of data that you have, depending on the type of studies that you're going to carry out, you can have different types of drought indices. I put an exhaustive list of drought indices. Probably you can I'll be sharing this PPT with you in your free time. You can go through and find out which drought index is suitable to your region. So these are many things that we have. Okay, you're fine. You have I classify into the first table is based on meteorology. The second table on the right hand side is based on the hydrology. You find the drought. There are many indices which are being used across the world, and many of these have been tested in India, because India is one country which has got periodically droughts. So we do a lot of work on this in India, and you find every year there's a demand by many states, many districts to declare the districts or states as drought affected to get more funding from the government to take care of the drought. So this is a very common thing that happens, and as people working in drought, we have to give input to the government to help to overcome the adverse impacts of drought. So these are some of the things. Then you also have, earlier I had given meteorology, then you have hydrology. Now, based on the soil moisture, you have certain indices, and of late, geospatial information also gives information on the drought. Using remote sensing, you got a vegetation index, you got a temperature condition index, you got vegetable condition index, and also vegetable health index. Many of these things are from the remote sensing point of view, and you find remote sensing and geospatial technology have changed the way we look at many of these things. In fact, the smart agriculture involves a lot of remote sensing and geospatial techniques. Now, most of the indices that we use, there are some standard drought indices which we commonly use. The standard drought indices, they take into consideration stationary condition where location scale parameters are kept constant. That means we keep the location and scale as constant, and then the standard drought indices, which which in our study we use, are the standard precipitation index, which is called SPI. It represents the deficit of precipitation in the study area, representing meteorological drought. So standard precipitation index is a part of meteorological drought. For SPI, precipitation is considered as the input variable, and the two parameter gamma distributor is fitted to precipitation series with constant local and constant scale parameters. Then you got the standard evaporation, precipitation evaporation index is again an extended form of standard precipitation index, taking into account the evapotranspiration. So here we talk about the water balance value, the evaporation and the potential evapotranspiration, and we use the well-known Hargreaves method to calculate the potential evapotranspiration. And this is used as input compute the standard precipitation operation index. And so we will see how things are being done. Then another one is the standard stream flow index. So here it represents the deficit of flow in the stream in the steady region. It basically takes care of the hydrological drought. So you find we also fit a log normal distribution to this. Then you got another one is soil moisture index. This is an agricultural drought index. So here again we fit our gamma distribution with constant location, constant scale parameter. Now when you have the drought value, you find some numbers are given here. These are depending on the index that you use. This is one example. Now depending on the number, the drought can be classified as extremely wet, severely wet, moderately wet, mildly wet, mild drought, moderate drought, severe drought, and extreme drought, depending on the drought index value that you're going to calculate. So what the various things that I told you, you can calculate and then find out what are the various types of droughts that we can have here. Now, when you talk about drought management, that's very important. When you have drought management, we have to receive the forecast, the early warning and advice from scientific communities and water managers. So for which we need to study the past drought, we study a lot of analysis so that we try to get drought information in advance, which is accurate. So this requires a lot of work and people are working on it. Then we also require information regarding crop characteristics and rotational crops, rotational practices. What crops are we growing? Are we using rotational crop? Because the moment drought comes, the land and water management, agriculture practice becomes very important. Then you replace lawn vegetation with native drought-tolerant plants. So we have to go for native crops, drought-tolerant plants. That's very important. In fact, in our country, unfortunately, we do not go for native crops. We try to get exotic crops from elsewhere and try to grow, but that is not good. Every crop that we choose must be suitable to the local condition, must be local to the total local soil, must be suitable to the local cultural eating habits of the people. So we unfortunately try to bring a lot of non-native plants and grow. That is not good. So we have to go in for native drought-tolerant plants. Then for drought management, another thing that is required is we have to have information regarding climate data, soil moisture data, stream flow, groundwater, then the details of a lake and reservoir. Then you have to have develop the key indices and composite drought indices. Then have green infrastructure, porous payments, which is now very common. That we try to have payments which are porous. That means water can enter into the ground, and this can slowly stuck in the ground, and ultimately develop a strong warning system so that farmers could be benefited. Today, there is a lot of things that is happening that we give drought warning, we suggest the suitable cropping pattern, and we help the farmers. And farmers are also knowledgeable; they demand a lot of things when you do that. Now, for the drought information, there are a few institutions which provide data. Indian Meteorology Department. These give information which can identify the meteorological drought for each state, considering for every year. They give it to, and they have been so successful that they are able to tell well in advance what is the meteorological condition that they're going to have. Then you got the Agricultural Meteorology Department, which gives very kinds of data related to agrometeorological parameters. Then many drought research units developing a pre-harvesting crop prediction model. In fact, most agriculture universities in India, Indian Council of Agricultural Research, they do a lot of this work. Then you have got institutions like Drought Area Study Investigation Circle. They got Center for Research in Drought Areas. Then you got a lot of organizations within the country which have been studying this drought condition. Then we got another center, the Delhi National Center for Medium Research Range Weather Forecasting called NCMRWF. They developed a lot of numerical weather prediction model to medium range weather forecast. And these models are available for us to use in academic area. In fact, interestingly, most data required for any research is available free of cost, provided we give it in writing that this data that we get from the Indian Meteorology Department or from NCMRWF will be used only for research and will not be used for any commercial purpose. So these data are generally given to us without any difficulty. Now, with the climate change, what happens? The effect on the crop development, increase in carbon dioxide concentration, increase in extreme floods, even like floods and drought, and increase in temperature and increase in heat. Some numbers are given here. You find there's an atmospheric impact so much. The gas is almost 80%, radiation comes around 50%, heat is around 60%. So these are various impacts on the earth by the climate change that is happening. Now, there are many models which are available now, which are available across, it's available without any cost, it's easily available. Something called a global climate model, GCMs. And in GCMs, we in our studies have taken up coupled model, intercomparison model, CMIP, 3, 5, and 6, phase 3, phase 5, phase 6. And we used 3 RCPs, RCP 2.6. RCP represent concentration pathways, which talks about the greenhouse concentration adopted by the IPCC. So we find they have taken up RCP 2.6 is 2.6 requires carbon dioxide emissions start declining by 2020 and go to zero by 2100. There's one condition. Then RCP 4.5, the representative concept part 4.5, require carbon dioxide emissions start declining by approximately 2045 and reach roughly half of the levels by 2050, level 2050 and by 2100. And then we got RCP 6, emission of peak around 2080 and then decline. And there are a lot of threats. Peak, of course, around 2100. That means 75 years from now, still there will be peak. So these are the 4 conditions that can be used, and these are details available in the 5th annual report, AR15. In fact, recently, AR6 also has been released, which is available free of cost for us to download and work on this. So let us look at the CMIP6 model. And today, this is what is being used. Here, the projected socio-economic global change up to 2100. If you just look at this, the CMIP6 coupled model intercomparison model, that is what we use. And here we have the shared socio-economic pathways. They have 245, 126, 370, and then 85. These are the 4 shared economic pathways that we use. So if you get SSP 245 means emissions high enough to produce a radiative force of 4.5 watts per meter square in 2100. And SSP 370 means emission high enough to produce radiative of 7 watts per meter square in 21. This is high forcing. Then you got SSP 126. That means radiation up to 1.6 watts per meter square in 2100. This is low forcing. And there's one more which you use 8.5 watts per meter square in 2100. That means we think about 2100 from now, that is 75 years from now, what is the projected socio-economic global changes, and that's what we are seeing. So these 4 models can be used now, and in India these have become very common. We try to use it. Now, when we do the analysis, we also have, because we don't get data for a lot of areas, we have to get some data and try to downscale for our region. We got 2 types of downscaling that can be used. One is called a statistical downscaling. It is based on a view that the regional climate is conditioned by 2 factors: the large-scale circulation, which is well resolved by models, and small-scale features like land use, topography, land use constraint. They're not adequately described by model. That means the large-scale circulation can be modeled well. The short, scale is not described in the model. So we find they try to develop empirical relationship linking large-scale information and local variables is being developed. So statistical study is what we do. Then we have what we call the dynamic downscaling. It's intended to lead this. It's used in the regional climate models and the atmospheric general circulation models, and these are suitable to provide global climate scenario. So there are groups working in our country on both statistical dynamic downscaling and dynamic downscaling. Then you also find when you get the data are biased. So the data must be done some bias correction. So you find the spatial resolution at which the global climate models are run is too coarse to get reliable projections at regional and local scale. So you find we require precipitation and temperature projections at higher spatial resolution for the climate impact assessment. So you can do the bias correction by linear scaling of the precipitation, and then distribution mapping, low intensity scaling of precipitation, and quantile mapping. These are some of the methods available for bias correction. Now, what happens when you have the cumulative effect of drought is the climate, drought, crop yield, all are interrelated. You find a picture here, we show the impact of drought. Now, next 30 minutes, I'm going to talk about one of the work that we have taken up with the three objectives. One is meteorological drought assessment under climate change. Then we talk about non-stationary assessment of drought, and we try to develop drought indices. So these are three objectives that we have taken up, and this has been taken up for the Godavari River. Godavari River is one of the rivers which has been studied by various groups in the country, and so it's easy to compare our results with others because Godavari is one of the most studied thing in the country. So the study area is the Godavari River, which covers. This is one of the largest rivers in the country. In fact, Ganga could be the biggest, but Ganga, when it starts, Ganga, it's not called Ganga. When it ends, it's not Ganga. The Ganga starts with two tributaries, main, Alaknanda and Bhagirathi, and before joining the sea, it divides into Padma and Hooghly. But this river, Godavari, is completely in India. And so you've got 3,12,810 square kilometers, and it originates at elevation of about 1,100 meters near Nashik and flows over 1,465 kilometers before it enters into the Bay of Bengal. It's one of the longest rivers in the country, covering many, many states. Okay, so the latitude longitude are given here, and it receives 85% of annual rainfall in the southwest monsoon, and the rainfall varies from 600 millimeters to 200 millimeters across here. So you find it covers many states, and there are many small tributaries also here. We got the upper region, then we got middle region. We got Varda, Vainganga is a tributary here, Pranita is a tributary, Manjira is a tributary, Indravati comes from Odisha side. Or ultimately they all join here. So you find the study area that we taken up is that. So why this river? So we try to find out the problem statement, and this over the years they found that this Godavari sub-basin which you have chosen have been experiencing severe drought periods due to climate variability over the past several decades, and they lie in the rain shadow region of Western Ghats and receives relatively less rainfall. So it's essential to study the drought so that the community's livelihood environment can be improved. So we try to propose an integrated drought monitoring index, take into account the non-stationary behavior of the drought indices. So the framework that we taken up is here. Now you find we try to develop one index here. Then you find construction of multivariate drought index, hazard drought index. Then try to find a correlation between standard yield residual series and SPEI. So you find you can look at these things in your free time. We used a very well-known model called SWAT, And from SWAT is useful to us to develop the construction of the multivariate drought index for future and the reference period. So we did require data for this. So we used a 0.5 into 0.5 degree monthly graded precipitation data, and these data were available for us, which is available to everybody. And we had the data for about 38 years, 2019, 18, 2017. And we got the data, we downloaded from the Indian Institute of Tropical Meteorology Pune website. I give a website here. All this can be downloaded from the regional climatic models. Then the data that we use are the daily precipitation and maximum minimum temperature data. They were downloaded from the IMD website. Then daily precipitation, maximum minimum temperature data for historical period. Then we try to take 2 periods before and after, and then we fought four SSPs, shared pathways I told you, SSP 126, 245, 30885, and they are obtained from the website that I given here, and the source are all here. So then we used to index called Dunn index and seal out coefficient. The Dunn index is the ratio smallest distance between observation, not the same cluster, like we need to have similar clusters. So we not the same cluster, the largest intrastructure cluster distance. And high D index means better clustering, number of clusters that maximum D is taken, the optimum number of clusters. Like the whole state is divided number of clusters, try to find what is it. Another one is a seal out coefficient, that how do we interpret and validate the data within the clusters, how well each subject is classified. So if you have a score of 1 denotes that the data point is very compact within the cluster to which it belongs. So first value is -1, values near 0 denote overlapping clusters. So these are the two indexes that we use. And you find that you find the Godavari is in here, and we find the Dunn index values here. We find 4.52 is got the highest, 8.1 is the highest, and corresponding seal out coefficient also is here, and we find this. So we find, based on this, we divide the whole into various climatic divisions. Then we try to, the SPI is developed for different climate divisions. This is what we got. We try to compare the historical period with the future time period, and RCP 4.5 and 4.6. So we find that's how that we got here, climate division 1, 2, 3, 4, 5, 6 here. These are based on this. And we try to compare historical and future drought characteristics. You find here the density and severity here, and you find different colors that we have here for different RCPs. And this we try to understand from the observed period. This actually observed. This is for the future, how it's going to change for different climatic divisions. So some equation that is there. We got the multivariate drought properties. Then we calculate the drought return periods that we can use. And we use some copulas, which are the most common copulas that we can use: Clayton, Frank, Gaussian, Gumbel, and students. These are available literature which you can study. I'm going to do this with you later. Now we found the drought characteristics of SPI computed based on trivariate cupola models. For different conditions, we find these are the values that we have, SPI values. Okay, for RCP 4.5, RCP 8.5, for different return periods, 5, 10, 20, and 50 is what we use here. And this is another T and years of drought characteristics, again for the similar climatic division that we use here. Now the observation that we found here is, overall, the frequency, duration, severity, and peak of droughts are expected to increase in future. That means in the future, we are going to have more frequent drought which is lasts for longer duration, severe, and the peak are going to be more. So the cupola analysis showed that the Gumbel and Frank cupolas performed well for most climate divisions by the two tests that we have. Then you find frequent drought events are observed in the climate division 1, 4, and 6. So you find basically that future we are going to have drought and we have to be prepared to take care of them. Then we try to use another drought index or non-stationary reconnaissance drought index and non-stationary standard precipitation index. The two things are given here. And you find here how the drought propagates from here. You find the drought in the month of January is like this. In May, you find is like this. That means green color says no drought, red color shows extreme drought, the yellow color so extreme, severe, moderate, and no drought. Okay, you find that's how it's going to propagate for two of the indices that we got here. That means it's quite encouraging. And here you find this is temporal. This also the other two indices are on three time scale. This is for NRDI and SRDI, and this is on a 3-month scale. And this is how, for again 2 periods, 2051 to 17, what is going to happen. So find the drought is going to be bad in the future. And we try to use some box diagram here. And you find that this basin Godavari is going to have a lot of drought in the future. So observation that we got here, the temporal drought propagation showed the western parts of the basin are highly susceptible to drought condition in the month of March, April, May, and the drought propagates from eastern to western part of the basin from the month of January to May. It means these 3 March, April, May are going to have severe drought, and severe droughts are higher in the western part of the basin. Then the two models, NSP and RDA, perform better compared to stationary models. The upper Godavari river basin showed significant influence at various lags. Now we also used two other sub-basins of Godavari, the Indravati and Vainganga. We tried to study the land use, land cover, soil and dam. These are the LULC soil and dam maps. And we try to use this using the SWAT model for runoff generation. So the various two sites we use, Pathagudam and Ashti, we use you find the R squared and NAC are pretty good in these two places. We use here. We use for Indravati river basin and Vainganga river basin. And you find climate projections are like this. That means here, the high and low values, you find that this area is going to be highly variable with respect to climate. And you find the temperature are going to be very high in part of the basin. That means the red color shows a high temperature, and the blue color, the red color shows high. 37 is the highest that you get here in different model that we have here. Similarly, mean annual temperature for the Vain and Vainganga and Indravati river basins are going to be like this. So you find that similarly evapotranspiration stream flow changes also we studied 1976 to 2013, and the future periods you find how the evapotranspiration and change stream flow takes place in the two basins. Then we try to develop the multivariate drought index. You find the green color shows high drought and the red color shows low. So you find many of these places the green colors are very high and low here. Then you want the similar one here for the Vainganga basin, the first one, and IRB was second one. So you find there's going to be a high amount of drought. The whole basin is classified as going to have frequent droughts. Now, once we know that these basins are going to be affected by drought, we can start taking care of them right from now by changing the cropping pattern suitably to take care of, to use the crop which are drought resistant. So that's what we have suggested here. So you find the southeastern part of Vainganga river basin and southern part of Indravati basin. Indravati basin comes from Orissa side. They are going to get high annual precipitation, and the annual maximum temperature also showed high precipitation and high temperature in the future. And you also find that because of high precipitation, you find there is a reduction in drought events in the future period. That means Venganga and Indravati are going to be slightly better. So let me stop here with some good quotations for you. This is something I always tell people, can you go 24 hours without complaining about anything? Then watch how things start growing. Then have a lot of positive thoughts every day. And when you work, you come across lots of people. There are people who you like, people who like you, enjoy them. People you like, but people don't like you, accept them. People, they like you, but you don't like them, respect them. And people you don't like and they don't like you, avoid them. And in any work that you do, show high amount of integrity, motivation, honesty, innovation, sincere hard work, and leadership. And let me stop here. This is you have my email ID here. In case you would like to ask any question, please do not hesitate to mail me. I'll give a reply within 24 hours if I'm free. And this is another picture which has developed a lake in Kerala which was purified without using any chemicals and pump and power. And that's a plant that we use to purify the water. The water we purified up to 90%. Thank you.
Thank you, sir, for a wonderful presentation and sir giving a lecture on drought and various different aspects, as well as sir, some of the very interesting slides in the last, so that we can motivate in the research and teaching professions as well. I would request, if somebody has any questions, please ask. If you have any questions, you can ask now. Interact with sir.
Question may be less because there are too much things covered in 1 hour.
Yes, sir.
But
yes,
I will share the PPT with you.
Sure, sir.
The
Sure,
students can go through it at their free time, and then they can mail me their difficulties. I will answer them.
Any questions, please? Okay. Somelji, over to you.
Yeah. So, okay. Thank you so much, sir, for such a wonderful talk. We have learned many things in the drought and how do we calculate, from the different index as well, from the different data sets, from the different, climate models. I hope students have also learned many things from this presentation. And if they have any questions, they will, sir, interact with you. I am very sincerely thankful to you, sir. Thank you so much.
I will share the PPT with you, just no problem. So
yeah.
I'll send it to your email ID.
Sure, sir. Sure. I'll share with them this presentation to everyone. Yes.
Thank you so much.
Thank you so much, sir. Thank you so much.
Thank you, sir. Thank you.